All right, so this is part 3 to the videos for section 4.1, and I'm just going to go straight into it. We're just going over more antiderivative examples or indefinite integral examples. So assuming you've watched the previous videos to this point, I'm going to assume you've seen those and already know what an indefinite integral is. So we're just going to be using the rules for integration. So number 15. All right, so the integral of x plus 7 and then dx. So one of our rules is that we can break this up as the integral of x dx and then plus the integral of 7 dx. And the rule for sort of like the power rule for integrals is if you integrate x to the n dx, that's equal to 1 over n plus 1, and then x to the n plus 1 plus c. And then if you have a constant integrating like k, it's just a constant, k dx, that turns into kx plus c. So for our example, we have x integrating x. That becomes x to the, so 1 over 1 plus 1, and then x to the 1 plus 1. So that takes based off that relationship. And then we have 7, and that's a constant, so that's going to become plus 7x. I almost wrote k. 7x, and then we got to attach our constant of integration at the end. All right, so make sure you always put the plus c. So what this is that's going to be 1/2 x squared plus 7x plus c. And again, make sure you put the constant of integration because we're dealing with indefinite integrals. All right, later on we will deal with definite integrals, and I believe it's section 4.4. Again, so we have the constant of integration plus c because this is a family of functions. The 1/2 x squared plus 7x plus c is a family of functions. That's the antiderivative, so that means when you take the derivative of that, you get x plus 7. All right, so the next one, number 17. All right, so normally, so I've been breaking it, decomposing it as the integral of x dx plus the integral of 7 dx. I'm going to just kind of skip this step and just kind of like, for instance, I would jump from here to here because we know we integrate each piece. All right, and it's just a matter of applying the rules. So I'm going to skip that in between step since we know we got to integrate the x to the 5 piece, and then we got to integrate 1. And we're using the same rules that we just used in the previous question, except this time n is going to be 5, so we're still using these same 2 rules. So I'm applying that one for the x to the 5th, and I'm applying this one for the 1, since 1's a constant. So this is going to be equal to, and again, so you add 1 to the exponent, so it's x to the 5 plus 1, and then you divide by that same value, so 1 over 5 plus 1. All right, that takes care of the x to the 5, and then plus, in this case, k in this is 1, so we 1 times x, and then plus c. So I hope that is clear. I just skipped the in-between step just to, because it gets, I mean, we know at this stage we integrate each component or each term. All right, so that's going to be equal to 1/6 x to the 6, and then plus x plus c. All right, next one's number 19. All right, so integrating each piece. Now for the x to the 3 halves, I'm going to still be using that same rule I've been using over and over again. I'm going to add 1 to its exponent. So well, x to the 3 halves plus 1. And then I do divide by that same value, 3 halves, 1 over 3 halves plus 1. Now the x, 2 times x, you can think of doing integrating 2 times x as you factor out the 2, and then you focus on integrating x. All right, so it's going to be plus 2 times the integral of x, and the integral of x is x to the 1 plus 1, and then divided by 1 plus 1. All right, so that same rule I've been using, and then when you integrate 1, that's like using the previous question where we had integrated 1, we get 1 times x, or just x. So that'd be plus 1x, or x, and then plus c. So now we simplify this, so we're going to have 1 over 3 halves plus 1. So 1 is the same thing as 2 over 2, so we'll be doing 3 halves plus 2 over 2, which is 5 halves. And then I have x raised to the 5 halves. And then here I have 2, and then the 1 plus 1 is 2, so I could divide out these, and that just gives me x squared. And then plus x plus c. And the 1 over 5 halves, you take the reciprocal of that, it's 2/5. So it's going to be 2/5 x to the 5 halves, and then plus x squared plus x plus c. So I'm using the same rule over and over again as far as the x's go. Just add 1 to its exponent and divide by that same value. The only added thing here that was different is we have 2 times x, and you just factor out the 2, focusing on integrating x. And that applies that same rule that we've dealt with. And then anytime you integrate 1, that turns into x because of the rule integrating k, dx turns into kx. Except this time k is just 1. All right, so that's number 19. Next one, number 21. That's integrating the cube root of x squared. So this one's a little tricky because I can't, there's no rule in the integration table that deals with the cube root or of something. So I want to rewrite this into a format so that I can apply what we know from the integration rules. And this requires knowledge from algebra. And anytime you have so from algebra, anytime you have the nth root of x to the m, that it could be expressed as x raised to the m divided by n. So it can be a rational exponent where the index, in this case here, 3 is the index. The index goes on the bottom of the fraction for the rational exponent. So applying that, I can rewrite the cube root of x squared as x to the 2/3. And then dx. And now I can apply the rule that we already know where we add 1 to its exponent. So that's going to be x to the 2/3 plus 1. And then you divide by that same value. So 1 over 2/3 plus 1. And then plus c. All right, so our constant of integration. 2/3 plus 1. Well, 1 is the same thing as 3 over 3. So you're doing 2/3 plus 3 over 3, which is 5/3. All right, then you're doing 1 divided by 5/3 as the reciprocal is 3/5. All right, so that's going to be it for that one. And really, you just had to know from algebra this rule where you change a radical into an expression that has rational exponents so that you can use the integration formula we've been using over and over again, where you keep adding 1 to the exponent and dividing by that same value. So number 23, integrating 1 over x to the 5th dx. And I'm going to have to rewrite this one also because x is in the denominator. But we know from algebra anytime you have 1 over, let's say, a to the n, that's equivalent to a to the negative n. So I can rewrite this as x to the negative 5th. And then apply that formula where we add 1 to its exponent. So it would be x to the negative 5 plus 1, and then over that same value, 1 divided by negative 5 plus 1, and then plus constant integration. That's going to be x to the negative 4th, and then we're doing dividing by negative 4. So it would be 1 over negative 4, x to the negative 4th, and then plus c. And then the last thing is make the negative exponent positive. So that just brings the x into the denominator. So we have negative 1 over 4x to the positive 4, and then plus c. Okay, so that's how we do that one. Now number 25 is a little bit more difficult. Because we have x's on top, x's on the bottom. So I'm going to see, can I rewrite this into into something different where I can apply the integration rules. So I'm going to rewrite first, then apply integration rules or formulas. We know the square root of x is x to the 1/2. So this would be x plus 6 over x to the 1/2. And by fractions, we can decompose this into two fractions where they both have x to the 1/2 on the denominator. So it would be x over x to the 1/2 plus 6 over x to the 1/2, and then dx. All right, so from algebra, if you have a fraction and you have a same variable up top and bottom, you subtract the exponent. So when you have x over x to the 1/2, that's the same thing as x to the 1 minus 1/2. And then here for the 6 over x to the 1/2, if I want to rewrite that into a format to where I can integrate, I bring the x to the top, and that changes the exponent to negative 1/2. So it'll be plus 6 x to the negative 1/2, and then dx. All right, so the x to the 1 minus 1/2 is x to the 1/2. And then I have the plus 6x negative 1/2, and then dx. Now I integrate each piece. The x to the 1/2, so that's going to be adding 1 to its exponent, so it'll be 1/2 plus 1, and then you divide by that same thing. So the 6 times x to the negative 1/2, you factor out the 6. So I'm going to put that in green, so factor out the 6, and then focus on integrating x to the negative 1/2. And that's doing the same rule that we've been doing over and over again. We add 1 to its exponent, so it'll be x to the negative 1/2 plus 1, and then divide by that same thing. So the first thing, we have 1 over 1/2 plus 1, so 1/2 plus 1. So you're adding, that's going to be 3/2. So you have 1 over 3/2, and then x to the 3/2. And then you have 6, and then times 1 over negative 1/2 plus 1, that's 1/2. And then x to the negative 1/2 plus 1, that's x to the 1/2. And then plus c. Then I take the reciprocal of these. So the reciprocal of 3/2 is 2/3. So you have 2/3. X to the 3/2. Reciprocal of a half is 2. So it'll be plus 6 times 2, and then x to the 1/2, and then plus c. And then you do 6 times 2 is 12. So you get 2/3 x to the 3/2 plus 12x to the 1/2 plus c. And that's it. That I'm fine with that being the answer. You could try to rewrite it if you want. So I believe the textbook actually has this as the answer. You could try to do some factoring if you want. Like I could factor out an x to the 1/2 and maybe a 2, but it's just going to be rewriting the same thing. So I'm going to keep it like that. All right, so the next video I will do trig examples of integration.